Let's pray. Father, please help us today as we're studying these things of physics and quantum mechanics. Help us with the math of it, but maybe more than that, help us with concepts to understand what's going on, to keep variables and constants straight in our minds. So these things make sense and can be related to something that's somewhat concrete. We're not just having to imagine all these things and be dissociated from them. Help me to be clear and to understand the things that I'm teaching well, that I can teach them well. Help us to be clear in our thinking, ask questions, be humble, wherever that's appropriate. We pray this in Jesus' name. Well, back to astronomy, not to chemistry. Here we go. Let's do this one. So last time I showed you guys a video, right, of some principles of quantum mechanics, kind of as a precursor to what's going on. We saw there's this wave-particle duality. Something like light and even electrons, they function both as waves and as particles. So a wave can propagate itself, and it can pass through, if I send out a wave and I put a little slit, it'll fill the space afterwards. It'll propagate itself out. A particle is just going to go through, right? If I have two slits, then a wave can pass through both slits simultaneously, and it can actually interfere with itself, and you get nodes and antinodes and all these things. Whereas a particle can't really do that. It just, it can fan out as it, bounces off of the thing it went through, and maybe at slightly different angles, but it can't interfere with itself. And yet, when we pass light through two slits, like in Young's famous double slit experiment, we see that light is passing through both simultaneously and interfering with itself. And so it has to have these wave-like characteristics, but it also has particle-like characteristics. So it's doing both at the same time, which that might not mean much to us. Like, we just take these for granted, and we absorb energy from photons and get excited to other orbitals, other energy levels. So it matters that way. We're energy levels. So it matters that way. We're also concerned with how light behaves, because in many ways it's how all particles, small particles, behave. Keep using this word quantum. So quantum, it comes from a root of quantity. So when we talk about hydrogen, right, how many electrons does it have? It's one. Where's that electron at? It's in the first shell. It's in the first quantum number. Any electron in that first shell, I don't care what atom you're looking at, it has a certain amount of energy. And if it were to bounce from that first shell to that second shell, it has to have another energy level, right? A whole other level. It has to absorb a certain amount of energy to go there. But these energies are discrete. It's an exact number. It's not like, well, I get close and I'll get close, or I'll have a little more, so I'll go a little above. It has to have absorb exactly the right amount of energy to go from the first orbital to the second. If it has more, has less, it needs to absorb exactly enough because of quantum mechanics and frankly things that are beyond my training. And when it falls from the second to the first, it releases a precise quantity of energy. Okay, this is where we get this idea of quantum physics, quantum mechanics, the quantum nature of electrons. That's where all this is going. But we gotta kind of build into it. We get to begin very gently with just some very, very simple physics. Just some simple problems like speed and velocity and wavelength and stuff like that. So we're gonna do that. I want you to calculate experimentally Let me throw some numbers at you. I want to calculate the speed of light. Let me get out some calculators here. So, oh my goodness. Speed of light equals lambda times mu. And so I've already done it, I've already thrown you in a hole, and you don't even know if I'm talking about what are these things. I mean, I can give you numbers and you can plug them in, but we do need to know these. So c as a constant is always going to be the speed of light. Lambda is always going to be wavelength. The Greek letter mu is always going to be, that's what I'm looking for. I'm wanting to say hertz, because hertz is cycles per second. What is wrong with me? Frequency. Wow. Even as we get into this, I think I need to not take anything for granted, okay? So these are some variables that we're going to be dealing with, and we're going to add lots to them. We're just going to have a growing list, okay? When we talk about wavelength, we look at a wave. We can pick any given point on this wave. I can have peaks. I can have troughs. I can spell that right. I just want to know from peak to peak, or from trough to trough, what's the distance? That's all I mean by wavelength, okay? For one complete cycle of that wave to pass through, what is the length of that wave? Okay. There are other things here. There's the distance between a peak and a trough. That's our amplitude. We're not so much worried about amplitude right now or today. And then we're interested with this concept of frequency. So if I pick a given point, okay, and I want to know frequency, what I want to know is how many waves are going to pass this point in a given unit of time, okay? We're going to record frequency as hertz, which is cycles per second. Okay? So if this had a frequency of 1 hertz, that tells me that this much of the wave is going to pass every second. If it has 2 hertz, it's going to be this many. If it's 3, and so on and so on. How many peaks or how many troughs pass through a given point in time, or a given point in space in a given amount of time. And I've given you this equation. I said, hey, the speed of light, well, it depends on the wavelength and it depends on the frequency. The speed of light is a constant thing. I'm going to give you that number in a minute. This does not change. These change. If I change this, then that has to change, right? If I change this, then that has to change. Light does not all have the same wavelength. We deal with long wavelength light all the time. Every time you're making a phone call, your phone's sending out waves of light that you don't see. Very long wavelengths. Long wavelengths are low energy, which is good. Otherwise, you'd be frying your brain. If you had an X-ray machine next to your face, the way that you have a cell phone next to your face, you'd be toast. Right? You know that you're only allowed to be exposed to so many X-rays at a given period of time. If you go get an X-ray, what does the X-ray tech do? They leave. Right? And And what do they put over you? A lead vest, so they only x-ray the part that you need. If you're a pregnant woman, they encourage you not to get x-rays. If you do have to get them, they're certainly putting something over the baby to protect it, right? So that you don't get exposed to these high energy, low wavelength light. Okay. But light all travels at the same speed. So if I increase my frequency, right? Excuse me, let me go backwards. If I shorten my wavelength, what's going to happen to my frequency?
Increase.
It's going to increase, great, right? If these are traveling at the same speed, but I've got this wave and then I've got this wave, well, if these are going at the exact same speed, it's fairly obvious that I'm going to get, you know, what is that, 1, 2, 3? It's about a 3-to-1 ratio, right? My speed's the same, my wavelength here is cut in half, my frequency is going to be tripled, right? It's going to be proportionate, okay? All right, we understand that, we're ready to move forward. I would like you to calculate the speed of light. I'm going to give you 450 nanometers at 6.67 times 10 to the 14th hertz. Nanometers, 10 to the what? -9. So this is 450 times 10 to the -9 times 6.67 times 10 to the 14th. What do you get?
Give me a second, I'll put it aside.
Okay, I'll take it.
3.00 times 10 to the
8th.
8th.
Good. That's really, really good. Okay, so you got 3 times 10 to the 8 meters per second. The actual value is 2.998 times 10 to the 8th meters per second, or meters second to the -1. Good. Good, good. So they want you to do a little bit with this. We can manipulate this, right? If C equals lambda nu, then we can go, okay, C over nu equals lambda, or we can go C over lambda equals mu. And so what am I saying here? I can solve for speed, I can solve for wavelength, or I can solve for frequency. All right, it's just manipulation. So this one says, hey, sodium street light gives off yellow light that has a wavelength of 589 nanometers. What is the frequency? Okay. Plug it in. This should be super simple, right? That's 589 times 10 to the -9.
tracking.
No, got a number? What do we got?
1.13 times 10 to the 21st power.
21st.
Yeah.
I really got that big number.
What'd you get?
I got, because it's negative 9 up here, I would call it 3, because like, to the 10 to the third,
Well, we're dividing by it though, right?
yeah,
So it's gonna make that top number much bigger.
yeah. Yeah, I did it wrong.
Okay, did you run it?
I did not figure out how to do it this time.
Okay. Okay, well, let's look at how to do it then. So we should have solving for frequency. So we've got 2.998 times 10 to the 8th meters per second, right? Meters, I'll go meters to the second, -1, that's the same thing, right? And now I want to put that over 589 nanometers. Now the one thing I have that I need to do left is I need to convert. So I want to go, this is in meters, this is in nanometers. So I can do it this way and go 1 times 10 to the 9th nanometers per meter. Right? Of course I could have just done this as 1.8 the other way. Either way, when I set it up like this, then I come out with an answer of 5.09 times 10 to the 14th cycles per second. Good?
Yeah, I know, I see where I messed up.
See where it's at? Okay. All right. Let's take another run at this. Let's do another problem. This type. We have, oh goodness. One of the frequencies used to transmit and receive cellular telephone signals in the United States is 850 megahertz. Megahertz, right? So that's hertz times 10 to the third. Okay. What is the wavelength? Oh, it's times 10 to the 6th. Is that right? Yeah, it's 10 to the 6th, guys. Megahertz is to the 6th. Because it would have been kilohertz to the 3rd. So that's going to change our number, right? So when you run this, what do you get?
About 3.527 times 10 to the negative 4, but that's right.
Times 10 to the negative what? Negative 1? No, that's not going to be right. Shouldn't be. Maybe it will be. I haven't done it. What'd you get? Get the same number?
Yeah.
You guys get the same number?
Yeah,
Yeah?
yeah.
Good. I'm sitting here going, well, that's not reasonable, but no, that is reasonable. All right, very good. What's next? We just did that. What else do you need to know? I would encourage you guys to read this chapter. Now, I can sit here and read everything in this to you, but that's going to be really, really boring. There's some very interesting stuff. Some of it is going to help some of this math make more sense, like these equations, like why are we doing them? It's going to help them make more sense, but I'm not going to read this to you. I really do want you to, if you will please go read it, it will help you. All right. Let's add some more stuff in. When we see light from a neon sign, we are observing radiation from excited neon atoms. If this radiation has a wavelength of 640 nanometers, so lambda equals 640 nanometers, what is the energy of the photon being emitted? So we need some equations for this, okay? Where do I want to go back to build into this problem? Okay. Our base formula for this is E equals H times mu. Now, in this case, E, as it always does here, is going to equal energy. Okay, so add that to our list of variables. H is new. H is going to be Planck's constant. Planck's constant has a value, a consistent value. It's a very small value. That value is 6.626 times 10 to the negative 34th joule seconds. This is telling us if I know the frequency, I can multiply that by Planck's constant and I can get the energy. That's not hard, right? So if I told you, hey, it's got a frequency of 14 hertz, you'd multiply 14 times Planck's constant, you get the energy, right? If I told you that it had a frequency of 5,000 hertz, you multiply 5,000 times Planck's constant. Since the constant is constant, then that makes sense then that a shorter wavelength energy, or shorter wavelength light, which has a greater frequency, hence a greater mu here, is going to have more energy. A longer wavelength is going to have lower frequency, therefore it's going to have less energy. Now, we were given wavelength. I don't have anything here for wavelength, right? But I do, because I have this other formula that we just did, which says C equals wavelength times frequency. So I can solve for this, and I can go C over lambda equals nu. Right? And now I can plug this in over here, right? And I can go energy equals Planck's constant times C over lambda. And I can solve for energy because I have lambda. So when I do this, what I actually get is energy equals 6.626 times 10 to the negative 34th times the speed of light, which is what?
2.998 times 10 to the 8.
2.998
9,
8 times 10 to the what?
8.
8, and that's meters per second, right? In this case, this was 6.626 times 10 to the negative 34th joule seconds. And here I'm given 640 nanometers, right? I'd love to just convert that into meters right now, so I'll go 640 times 10 to the negative 9th meters. When I do this, my meters will cancel, my seconds will cancel, and I'll be left with joules, which is exactly what I want. So I run this equation, and I'll get my answer. So go ahead and plug that in. To do that, I'm going to put in the speed of light here. Okay.
I just do the notation.
I got, 3.10 times 10 to the negative 19.
Very good. That's it. Okay. You good?
Yeah.
Good. Okay, let's show a problem like it. The microwaves in an oven are of a specific frequency that will heat the water molecules contained in food. This is why most plastics and glass do not become very hot in a microwave oven. They do not contain water molecules. This frequency is about 3 times 10 to the 9th hertz. What energy do these photons have? Okay, so I've been given hertz. It's my mu. I want to know their energy, right? So this one's actually, why this wasn't the first problem, so that's the second one I do not know. This one's straightforward. So I multiply Planck's constant, 6.626 times 10 to the 34th joule seconds, times, is this hertz or meters? Times 3, times 10 to the 9th hertz. How do I do it? Did I do this wrong? Oh, this is negative. Okay. Negative 34. No wonder it's in there. Well, that doesn't make sense. The answer is
19.878 times 10 to the negative 25.
okay. So I'm going to convert that. I'm going to say 2 times 10 to the negative 24th. I put sig figs in simple scientific notation. Good. Very, very good. All right. Now we get real. to give you the problem, then I'm going to teach you the things that go into the problem so we can understand it. Which I guess is what I've been doing today. Early researchers were very excited when they were able to predict the energy of an electron at a particular distance from the nucleus in a hydrogen atom. If a spark promotes the electron in a hydrogen atom into an orbit where n equals 3, what is the calculated energy in joules of the electron? So here's the deal. I've got my nucleus, right? And now I've got a series of orbitals, a series of energy levels, right? Each of these is quantized. So we want to know this. If a spark promotes an electron in a hydrogen atom into, so we were here in the lowest, right? Here's my electron hanging out. And it goes to n equals 3. This is n equals 1, this is n equals 2, this is n equals 3. So I got to throw in the word n here, okay? So n is the quantum number, the principal quantum number. Okay? So for hydrogen, n equals 1 is just hanging out down here, n equals 2 would be getting excited to the second shell, and n equals 3 is getting excited to the third shell. It's saying, hey, we're going from N1 to N3, find energy. So we need to understand some things about this. We know what energy is. Our formula to solve this is energy equals negative K times Z squared over N squared. Well, right now we know what E is, and we even know what N squared is. So if I had to do this right now and set this up, I'd go, all right, E equals something I don't understand over what value? 3 squared, right? Because I understand that that's my third orbital. Okay? But I have no idea what K is. I don't know why it's negative. And I don't know what Z is. Okay? So this formula works like for hydrogen. It does not work for calcium. It does not work. This was, in the book, they're taking us through the discovery of these things. And so they were working primarily with hydrogen at first, but then they find, okay, we solved this for hydrogen, but it doesn't fit other places. And they try to find models, okay, how do I take what was true in hydrogen and develop general principles that apply to all elements, or formulas that apply to all elements. And so it was a progression, and they're kind of walking you through this in the text. We don't have time to do that right now in class. I'll turn this into a history class instead of a chemistry class. But you do need to understand the math behind it all. So we know what N is. We need to know about K and Z. Z is going to be basically our atomic number. So we'll write that and I'll explain why this matters. Because we could just say times 1, or actually we could just leave it out at all if we were only concerned with hydrogen. But they found that they could calculate the energy for hydrogen. They found they could calculate it for helium so long as helium only had 1 electron. They found they could calculate it for lithium so long as it only had 1 electron. They could calculate it for beryllium so long as it had only 1 electron, but the energies were different. They could calculate precise energy jumps or energy releases for each of these atoms as long as they had only 1 electron. But they were different for each of these elements. And the difference between them was the charge that was happening there in the nucleus. So there's only one, it doesn't take as much energy to basically have enough escape velocity to go to the second level in hydrogen, where there's only one proton, as it does in helium, where there are two, or in lithium, where there's three. It takes more energy for it to go ahead on up. That makes sense, right? And so what is that relationship? Well, it's found by the square of that. So if we're doing this for, are we doing hydrogen? Okay, then our Z is going to be 1 squared, right? That's easy. If we were doing helium, then this would be 2 squared. Now, what is K? K is a constant. It was constant among all of these atoms if they only had 1 electron. And so they determined this experimentally. And the value of K is 2.179 times 10 to the negative 18th joules. So when I plug that in over here, I just go negative, right? Negative because it's absorbing energy. So we're jumping from the first energy level to the third energy level. That means we had to absorb it. So it's negative. So negative 2.179, and now I'm out of space, so I'm going to erase. Negative 2.179 times 10 to the negative 18th joules times 1 squared, because it's atomic numbers 1. And then I divide that by 3 squared because I'm going to my third energy level. And then you run that math, and we'll have an answer, and it'll be good. I think I made that make as much sense as I'm able. Now you get to listen to me low notes. Now remember, you have a test next week, right? I always think these are going to be shorter class periods. I'm always naive. It's all good. I'm going to throw that over. Have at it. Where you from? Do you have to ask to go to the bathroom like in high school or in grade school or anything like that?
Well, they say no. They say like, oh, if you need to go, just
go.
walk out. But everybody asks anyway.
Okay. Just
I think
polite.
it's common to ask. Because I don't know if it was kind of disrespectful to just like walk out. Feels like you're just walking out of the class. But most people did, instead of asking, was just like, I'm going to the bathroom, just like letting the teacher know.
Yeah, that's good.
Are we supposed to get a negative number?
Yeah, it'll be negative. Yeah, this sign's going to, because remember, we're absorbing energy here. So what'd you get?
Negative 2.42 times 10 to the negative 19.
Yeah. 2.421 times 10 to the negative 19 joules, right? So that's the amount of energy. So this is how much energy it has to absorb to make that jump. Okay, that's good. Let's do another one. Okay, so that same electron is now promoted to n equals 6. Find its energy. temperature? Okay.
Negative 6.052 times 10 to the negative 20.
Okay, hold on, say it again.
6.052 times 10 to the negative 20.
What'd you get?
Same.
Okay. Guess I answered or something. We did one correct. Okay. Very, very good. Well, let's do this next one. I feel leery of going forward with him out of the room, but we gotta move. Okay. What is the energy in joules and the wavelength in meters of the line in the spectrum of hydrogen that represents the movement of an electron from Bohr orbit with n equals 4 to the orbit of n equals 6? So we're going from n equals 4 to n equals 6. So I'm looking at the change, right? Not the energy for 4 or the energy in 6, but what's the difference? What does it take to get from 4 to 6? Right, so this is a change in energy. So I'm not going, hey, it's not going to be quite the same where it's like E equals kz squared over, what is this one?
N.
Is this n squared? Okay.
That's correct.
Okay, I'm actually looking for delta E, right? I'm looking for delta E of going from 4 to 6, yes? So I need to do it this way. It equals K times, what is my Z in this case?
1.
Hmm?
Is it hydrogen? So it's 1.
Yes,
It's 1.
times 1 squared over n squared is,
36.
we're going from 4 to 6, right? So it's, and we're jumping, so it's going to be negative. So I want to start with my lower energy level, so I want my 4. So that's going to be 16, right? Minus K times 1 squared over 36, right? Now I need to plug in K and run the math. I should be good. I can factor out K, by the way, right? I can run this whole thing and I can go, it equals K times 1 over 16 minus 1 over 36, and that should simplify my process. Let me go, hey, that equals 2.179 times 10 to the negative 18th times 1 over 16 times, or minus 1 over 36. Back. So what we're doing now is we're just looking at, all right, what is it, how much energy does it take to change from n equals 4 to n equals 6? So instead of just our base formula, we're using a,
Difference.
yeah, exactly. So it's for 4 to 6, so I go K times 1 over 16 minus K times 1 over 36. If I want, I can factor K out. That'll help with putting it in the calculator. K times 1 over 16 minus 1 over 36. Plug in the value of K. What do I get? Delta E equals, should be negative. In joule.
Is the 2.179 supposed to be negative as well?
No. I don't believe so.
Okay.
No. And actually, they're not even asking for a negative. They're just, it's basically an absolute value. They're just saying, what is the energy difference?
Where did the 16 and 36 come from?
Ah, because of my n. So I'm in, I'm beginning in the fourth.
Okay.
Yeah,
I forgot the square thing.
No problem. So what'd you guys get?
I feel So negative 7.6 times 10 to the negative 19.
Something's off there just a hair. Should be negative 7.566
Okay.
times 10 to the negative 20. Negative 20th though.
Yeah, because I did one of this.
Okay.
I did it wrong too.
I got you. You guys feel good? Ingrid, how you doing? Which route did you go? Did you solve for each of these individually, or did you factor out K?
I solved them individually.
Okay, so K over 16 minus K over 36. What was this value?
Because in my calculator, you can put them together, and I will do it all for you. But I think I put a value in wrong.
Okay.
It's not off by a lot, but I'm pretty close, so it's not like insane. It's okay. I know where I'm wrong.
You sure?
Yeah.
Okay. I've been doing natural log. That's why my last number, I hit the wrong. It has it as a secondary function, and I'm hitting the wrong thing. I'm like, that's crazy. All right. All right. Well, let's roll on. Let's do the next problem. What is the energy in joules and, oh, we can calculate the wavelength. Let's calculate the wavelength. Let's do that. So we know our energy, right? What does it want with the wavelength? Let me ask. Make sure that first. What is the energy in joules and the wavelength in meters of the line in the spectrum of hydrogen that represents the movement of an electron from 4 to 6? Okay, so if this is my energy, what is my wavelength? That's the question, right? So it'd be nice if we had something that represented energy and wavelength, and we have that, right? What's that formula? Energy equals H times frequency, right? But I don't want frequency, I want wavelength, so E equals HC over lambda, right?
Yeah.
So now I just need to flip it, so I get lambda equals HC over energy, right? So we should be able to solve that. So what's, I guess let me erase all this, that's a lot of stuff on the board. I'll leave my energy there at the bottom so I don't forget that. All right. Okay, so H is what value? H is 6.626 times 10 to the negative 34th joule seconds. And I want to multiply that by the speed of light, which is 2.998 times 10 to the 8th meters per second. So those will cancel out, so I'm left with joule meters at this point, right? And then I need to divide this by energy, which is 7.566 times 10 to the negative 20th, right? Make sure that I'm on the right track here. Joules. Okay. Well, that's good. Joules, seconds, that'll leave me with meters, which is what I want wavelength. So,
One question.
yeah.
Because the energy is negative, it will give a negative number.
Yeah, so the energy is not negative. It depends on how you're looking at the question, right? So if we're saying what is the change in energy or whatever, what does it take to go from 4 to 6? Well, that's a negative value, right? Because we have to absorb energy to make that jump. If we're saying, hey, it absorbed light to do this, that's the source of the energy, then we're going, what's the energy of that light? Well, it is that value, right? It's an absolute value at that point. And what's the wavelength of that light? I don't need to worry about the negative sign.
Okay.
All right, so I throw this in, and what do you get?
I got 2.62 times 10 to the negative 6.
Good. Very good. 2.626 times 10 to the negative 6 meters. Good, good, good. Okay, well, let's do another one. What is the energy in joules and the wavelength in meters of the photon produced when an electron falls from n equals 5 to n equals 3 in a helium ion? And we want to find energy. And we want to find wavelength. Okay? So my formula, again, if you will remind me, is something like E equals, this constant is a K?
Yeah.
Negative K, right? Negative K
Z squared.
times Z squared over N squared. Okay, so, since this is find the difference, right, delta E, I know that I'm actually going to be doing this. I'm going to be doing K times, what is my Z squared for my 5, right, is going to be 20, oh no, I'm sorry, my Z squared is for helium, right? So it's 2 times 2 is 4. Right, so this is K times 4 over, I want to do N equals 5, so that's 25. I want the difference between the two, so it's times K times 4 again, over 9, right? I can factor this out, and I can go, okay, it's K times 4 over 25 minus 4 over 9. And that'll give me my value. You know when you got it.
Is it, negative 6.198 times 10 to the negative 19?
Yeah.
I got,
Well, I'm sorry, it's not going to be negative, it's going to be positive.
I got positive 6.1.
198
Yeah.
times 10 to the negative 19. Just a conceptual check, we're going from 5 to 3, so we're releasing it. Good. Okay, now we want to find our wavelength. So we have our E. Remember our formula is E equals H over V.
H times.
HV, okay. Thank you, sir. equals hv. Subbing that out, I can go E equals h times c over, oh no, I don't need to do that.
T over lambda.
Lambda, okay. Right, and then if I want to solve that further, then I get hc over E equals. Okay. So, I know H, I know C, I know E, I plug those things in. H is 6.626 times 10 to the negative 34th. C is 2.998 times 10 to the 8th meters per second. This is 5. This is joule seconds, right? Okay. And I divide that by my energy, which is going to be in joules, which I just calculated to be 6.198 times 10 to the negative 19th joules. Joules cancel out, seconds cancel out. I'm left with meters. That's going to give me my wavelength. What is that?
3.205 times 10 to the negative 7.
Y'all get that? Get that?
I'm writing things down.
It's all good. You want a second on the formula? Or on the map? On there. Okay. All right. Erase these, do our next problem. Okay. If an electron travels at a at a velocity of 1.000 times 10 to the 7th meters per second and has a mass of 9.109 times 10 to the negative 28 grams, what is its wavelength? Okay. Well, we've been talking about light, and now we're talking about electrons, but we're still talking about wavelength. So, essentially, what we're saying is that anything that's moving, any velocity, is moving as a wave, whether we can see that or not. If you're talking about like something like throwing a baseball or shooting a bullet, you know, if you were to shoot it without gravity, there's no effective gravity, you're just shooting it out into space, it's not going to travel in this perfectly straight line. Now, we perceive light as traveling this perfectly straight line, but it's not. It's doing this, right? It's saying, this is saying that a bullet would do that same thing. It's saying that an electron is doing that same thing. Now, the wavelength for a bullet is going to be huge because it's a huge object, okay? But the wavelength for an electron, it's a tiny object. It's a lot bigger than light, obviously, but it's a tiny object. So it has a wavelength that we can talk about, we can quantify very, very readily. And so we've been drawing, we've been picturing electrons as moving around essentially in a circular motion. Well, that's like saying that the bullet's traveling in a straight line. In reality, it's not. In reality, our electron is doing probably something more like this. it's moving as a wave. Now we're curving that wave because of the influence of this positively charged nucleus. We've got some angular momentum coming in. Also, it's moving around this with angular momentum as a wave. Okay? If you got rid of this, that electron would just fall out into space, right? Okay. That said, and thank you, Lord, for helping me say that well, I think. I literally was just praying that you help me. I'm like, I'm in trouble right now. So this electron has a velocity, right? So the speed that it's moving at. We've been dealing with velocity. We've been dealing with velocity of the speed of light, right? Okay, so now we've got a different velocity, and it has a mass. We've not been dealing with mass before, right? Because light is massless. So we want to know its wavelength, and we have a formula for this. I'm not kidding. I was staying at the board racing, praying, Lord, please help me. Lambda, that's wavelength, right? Equals, here's Planck's constant again. So we're applying these wave mechanics and these quantum principles to things that have mass for the first time. Equals mass times mu, and mu, of course, is our frequency, right? So if I were to think of this, I can say wavelength equals Planck's constant divided by my mass times my frequency. Is there anything you needed to understand about that? I think that's pretty straightforward, okay? So this is looking at how quantum particles larger than light move. So just as we think about this a little bit, an electron, well, how do I want to say this? Think about this, as our mass increases, right? My wavelength, is it going to increase or decrease?
Decrease.
It's going to, what did you say?
Decrease?
Decrease, right? Because this is in the denominator. Right, so if I maintain constant frequency, then my wavelength is going to have to as mass increases, it's going to have to decrease, right? That makes sense. So something like a proton, if it's coming at the same frequency, right, it's going to have to be moving really fast in between. Or conversely, if I stay with the same type of particle, right, as if I want to keep my wavelength the same, then my mass, excuse me, let me say that backwards. If I'm staying with an electron, but I want to increase my velocity, or my frequency, that is, right, then this number is going to get bigger than my wavelength is necessarily going to have to get smaller. Okay? So just to conceptualize this a little bit. This is my formula, and here's what I've got. If an electron travels the velocity of, now I have velocity here, I don't have velocity there, so I have to have a means of getting to velocity. So I can do that. I have another formula that I can plug in here. Is that right? Maybe saying this incorrectly to you. It's not helpful for you. We use this equation to solve the problem, but you need to use a unit conversion for Planck's constant. That's where it's at. So Planck's constant is 6.626 times 10 to the negative 34 joule seconds, right? But that can be written differently, because a joule can also be written as 1 kilogram meter squared per second squared. And so you can rewrite Planck's constant as h equals 6.626 times 10 to the negative 4th kilograms meters squared per second. I'll have that written down. Go ahead and get that. So, when I go to do this, right, and what am I solving for again?
For lambda.
So lambda equals Planck's constant, but I'm going to write that out, 6.626 times 10 to the negative 34th kilogram meters squared per second over my mass, 9.109 times 10 to the negative 28 grams times 1.000 times 10 to the 7th meters per second. And now I can solve this.
You need to convert the grams to kilograms.
Yes, I do. So when I do that, thank you, sir. So when I do that, this is going to be times 10 to the negative 31st kilograms. So now my kilograms will cancel. My one of this is meters squared divided by meters, so one of my meters will cancel. I'll get left with meters, right? And per second time divided by per second is going to cancel. So I'll get my answer in meters, which is what I want. And when I run this out, I do the math. The answer is this is our last problem today. I didn't even finish what I meant to do. .274 times 10 to the negative 11th liters. Tricky part to this is to remember Planck's constant and convert those units. I strongly suspect I will not give you a problem like that on the test because I don't need to kill you on something when there's already so much to know. All right, you'll have a wonderful day.